Next problem is again the applications of Newton's laws for rotating objects. Consider a hollow sphere rolling down an inclined plane with a 45-degree angle to the horizon. If the sphere has a mass of 0.1 kilograms and a radius of 0.1 meters, what's the acceleration of the sphere as it rolls down without slipping? So to begin, let's draw a simple picture. Right? This is a inclined plane with a 45-degree angle with respect to the horizon. On top of this inclined plane, I put a sphere, which is hollow, right? And this sphere is going to rotate. It's going to be rolling down this inclined plane. Okay, so first things first, let us write down what the moment of inertia for a hollow sphere is, right? So you can look this up or you can calculate it. But the moment of inertia for a hollow sphere is 2/3 mr squared. Always mr squared. The only question is what's the number out in front. Okay, now this sphere here has a mass of 0.1 kilograms and a radius of 0.1 meters. All right. Okay, so let's basically begin by writing down all the forces here, right? So there's going to be a normal force on this object, which is going to be mg cosine theta, and then there's going to be f of x force. Let's choose this to be our x direction. So the sum of the forces in the x direction is F net x is going to be equal to, well, there's two forces here. There's this F of x, right? And there's also a force of friction, which is allowing this object to roll, minus the force of friction. Okay, so this is going to be equal to mg sine theta minus the force of friction, right, is equal to what? F net x, the mass, times acceleration, right? Okay, so that's the first part. Now, this thing's also rotating. The force of friction is causing it to rotate, so we have to sum up all the torques as well. So the sum of all the torques is equal to torque net is equal to basically I times alpha, which is what? The sum of the torques is just simply going to be the force of friction times R, right? Wherever R might be. Okay, so let's solve this equation first, right? I is going to be 2/3, all right, mr squared times alpha. Now, something carefully needs to be considered now, right? Which direction is positive alpha, right? So usually I like to think of things in terms of rotating in the positive counterclockwise direction, right? But in this case, well, we'll just keep it that way, right? We just need to map the difference between acceleration along this way and what the positive rotating direction. So if this thing accelerates, then in fact what happens is that it actually accelerates in the negative direction. So the difference is that alpha is equal to minus a over r, right? That's something we're going to use in just a second, right? So let's plug that into here. This is going to equal to basically 2/3 mr minus a over r squared. So the r squares will cancel one of these things out. This is going to be equal to the force of friction times r. Oh, lo and behold, the r's will cancel out on both sides now. All right, beautiful. Okay, so now I have, and this should be a overall minus sign because remember, x direction is in this way positive. Okay, so I get something that looks like 2/3 ma is equal to the force of friction. Okay, let's take this, plug it in there. All right, this m, all the m's are the same. So what I end up getting is m times g times sine of theta is 0.707 minus 2/3 ma is equal to ma. All right, the m's all cancel out. Let's bring this aside. This is going to be 5/3 a is equal to what is 0.7 times g. Let's figure this thing out. So 0.707 times 9.8 is equal to 6.9. 6.9 is equal to 2/3, 5/3 a, which means divide by 5/3, which is the same as multiplying by 3/5. And then I get a is equal to 3/5 times that times 3/5 is 0.6, 4.2 meters per second squared. All right. Okay, I hope that